So it says we are going to be doing a titration. What's a titration? What does that mean?
Is it something with like finding the concentration?
Right, it's a technique to determine an unknown concentration. And you can figure out an unknown concentration by using something with a known concentration, because we have pretty much figured out that if you have a known concentration and you multiply that by a volume, that's going to equal the concentration of something unknown, let's call it X, times a volume of that thing. So if we have a known volume of something that we don't know the concentration of, and we have a volume of something we do know the concentration of, it's just a quick and simple calculation to figure out what the unknown concentration is. And this is a technique that's used all the time. It's like in every lab in the world does these routinely. So it's a good thing to know how to do and how to understand how it works. But this is slightly different. This is a unique titration because we're going to be using redox or reduction oxidation. What's a reduction and oxidation reaction? What does a redox reaction mean? What does that refer to? What's special about a redox reaction, an oxidation reduction reaction? I haven't got the chat open, so you'll have to actually say it out loud. Redox. Anybody have an idea what redox is? Okay, it's going to be that kind of night. Fair enough. So what's an oxidation number? I'll put it that way. What's an oxidation number? What does that tell you? Something to do with electrons, because it's chemistry. Everything's got something to do with electrons.
Is it the electrons that are like gained or lost?
Right, there you go. Exactly. That's what a redox reaction is. It means that some atom is losing electrons and some other atom is gaining them. So the one that is losing electrons, we say is being oxidized. So its which meaning its oxidation number goes up. And so the oxidation number, if you were sort of think back, if that's possible right now, I know it's kind of tough. But the oxidation number basically tells you how many electrons that an atom can claim for itself, that it owns all by itself. So if you have something like carbon bound to oxygen, oxygen has a higher electronegativity, right? Oxygen steals electrons from other atoms. And so oxygen basically claims all of the electrons that it has itself, and it also gets to claim the electrons it's sharing with carbon because it has a higher electronegativity. So out of these 8 electrons that I'm showing you here, oxygen would get to keep all of them, and poor little carbon would get none. So we calculate oxidation number by how many electrons, how many valence electrons an atom usually has, and how many it actually has here. So in this instance, oxygen usually has how many valence electrons? What group is oxygen in?
6.
6, right. And it actually has 8. So we would say it should have 6. It actually has 8. So its oxidation number is -2. Carbon has none. It usually has 4. We would say that the carbon would have an oxidation number of +4. So in an oxidation reduction reaction, someone's oxidation number goes up, that's the one being oxidized, and someone's oxidation number goes down, that's the one being reduced. And in this reaction, vitamin C is going to be oxidized, and the thing that oxidizes it is going to be reduced. And we'll be able to follow the reaction because the titrant, which is the thing that we use to calculate a concentration, that's the known thing, is actually colored. And when it gets reduced, it changes color. It goes from being blue to being clear. Or is it the other way around? I think it goes from being blue to being clear. So what we're going to do is when you do a titration, we develop a standard curve. Want to tell me what a standard curve is? What does a standard curve mean? What do we do when we develop one of those?
Is that like a bell curve?
Not quite. No, it is data on a curve, but it's not bell-shaped. It wouldn't be shaped like this. It actually would be shaped like this. Hopefully, because it's not really a curve. Hopefully, it's not a curve. It's a straight line. But when we make a standard curve, what is it we're trying to do? You see, look right here. So it says we develop a standard curve using solutions of vitamin C with known concentrations. So basically what we're doing is we're plotting something against known concentrations of vitamin C. So that's what we're doing. So you have known concentrations of C here. And then over here, we're going to have volume of our titrant. And that's what we're going to show next. So that way, when we have something that's unknown, we'll take that volume of titrant and we'll say, I don't know what my concentration is, but I do know that my volume is this. That's how much volume it took to titrate it. So all I have to do is go across to the line and then go down. That will tell me what my concentration is. Okay? All right, so this is what we're going to be using to do the titration tonight. So this is called DCPIP, or 2,6-dichlorophenol-lindophenol, which is really easy to say. Basically, it has two phenol groups. You can see there's one here, and there's one there. And when it's reduced, when it gains electrons, you can see that this reaction is, it's oxidized over here, and it's reduced over here. So when we start, it's going to be blue. So this is a blue color when it's oxidized. And you can see that the two places it's oxidized are right here. This nitrogen, oops, let me go back. This nitrogen gets reduced, and this oxygen gets reduced. So each of them gets an electron. So you can see where before the nitrogen had a double bond, now it has 3 single bonds and a hydrogen. So hydrogen typically goes where the electrons go to balance out the charge. Because if you don't balance out the charge, then this thing, when it's reduced, would be -2. And so basically the protons go with it to balance out the charge. So this is the structure that gets oxidized right here. when we add it, so it's already oxidized. When we add it to the vitamin C then transfers 2 electrons over to DCPIP, and it goes from a blue color to clear. And so we'll know when all of the vitamin C has been oxidized when we start seeing the blue color reappear, because it should be clear, 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 clear as it's being reduced, 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 reduced. Then when there's no more vitamin C to be oxidized, then it'll turn blue. Then we'll see a small bit of blue again, because basically it means we're adding the blue version and there's no more vitamin C for it to go back to being the reduced. Now I'm going to compare that to an acid-base titration. Now with an acid-base titration, we have H plus and OH minus, and they come together and form water. That is the classic neutralization reaction. So I have a question for you guys. Is this a redox reaction? So I want you to think about that, because here I've got H plus, oops. I've got H plus, I've got OH minus, and it makes water. Is that a redox reaction? If it is a redox reaction, then the oxidation number should change. If it isn't a redox reaction, then the oxidation number should stay the same. So what happens to the oxidation numbers of hydrogen and oxygen on one side of the reaction and on the other side of the reaction? What's the oxidation number of the hydrogen right here? That one. If you have a single ion, what's the oxidation number? So H plus, what's the oxidation number of hydrogen when it's at H, when it's H plus? We don't remember our oxidation numbers, do we? So remember, a single atom ion, its oxidation number is the same as the charge of the ion. So what's the charge of the H plus ion?
1 plus.
1 plus. So what's its oxidation number?
1 plus.
Okay, there you go. So the oxidation number of this hydrogen is +1. Now we have hydroxide ion. So if now we have an ion with 2 atoms in it. So if you have 2 atoms in it, then the oxidation numbers of the 2 atoms, when you add them together, have to equal the charge of the ion. So in this instance, I have an oxygen and I have a hydrogen. When I add the oxidation numbers together, they need to come out to -1, because that's the charge of the hydroxide ion. Who has a higher electronegativity, oxygen or hydrogen?
Oxygen?
Sure is. Oxygen is the second most electronegative element on Earth. There's fluorine and then there's oxygen. So basically everybody is less electronegative than oxygen, with the exception of fluorine. So oxygen is much more electronegative. So these two shared electrons, oxygen's claiming those. So oxygen's keeping them. So what's going to be the oxidation number of the oxygen if it has all the electrons? So if it has all the electrons, it then would have 8 total. It has those 3 lone pairs around it, that's 6, then it gets to keep 2 for the bond. So how many valence electrons does oxygen usually have?
6.
And if it has 8, what's its oxidation number?
2.
-2. -2, because basically it has 2 more electrons. Electrons are negative, so -2. So the oxygen has an oxidation number of -2. So if the oxygen in hydroxide ion is -2 and the overall charge is -1, what does the oxidation number of the hydrogen have to be? Remember, they have to add up to -1. -2 plus something equals -1.
+1.
+1, right. And hydrogen is almost always +1, unless it's bound to something less electronegative, like if it's bound to a metal or something, it's almost always +1, because its electronegativity is around 2. It's sort of in the middle. And so metals have a lower electronegativity and non-metals have a higher. And usually it's bound to a non-metal. So it's usually always +1 because it only has 1 electron. So it either has it or it don't. So it's always pretty much always +1. But then when we look at water, again, oxygen is more electronegative than either of those 2 hydrogens. And so these 2 electrons in this bond and these 2 electrons in that bond, they're going to oxygen as well. So again, oxygen has all 8 electrons and the poor little hydrogens have none. So if oxygen now, same as before, has all 8 electrons, what's its oxidation number going to be?
-2.
It's going to be still -2. Hasn't changed, right? It's still -2. And the hydrogens, poor little hydrogens, have no electrons. So what are their oxidation numbers going to be? The other way you can figure it out is water has no charge. So the net charge of water is 0. And remember, all the oxidation numbers have to add up to whatever the charge of the molecule is. In this instance, it adds up to 0. So if oxygen's -2, what must the 2 hydrogens be?
+1.
They each have to be +1. So you can see this isn't a redox reaction, because even though we have electrons moving around, oxygen has them and oxygen keeps them. So it isn't a redox reaction. This is a redox reaction we're doing with vitamin C, because actually electrons are physically moving from one molecule to another. So that is the difference. So this is what vitamin C is going to look like. So you can see it's a much smaller molecule than DCPIP. So this is it here. It's fairly small. So when it's reduced, this is the reduced form on the left. And then you can see when it's oxidized, this oxygen goes from having its own goes from having its own hydrogen to then being double bonded. Same with this one. Goes from having its own hydrogen to then being double bonded. So it's basically losing an electron in doing that. And then, so these two electrons then get donated to DCPIP. And then we see the color change. So this is the overall reaction. So we start with oxidized DCPIP and reduced vitamin C. Then electrons move from, they're lost from the vitamin C. When you lose electrons, you're being oxidized. So this is the oxidation part of the reaction. In every oxidation reduction reaction, someone got to get oxidized and someone's going to get reduced. So this is the oxidation part of the reaction where electrons are lost. This is the reduction part where electrons are gained. So, and they always have to balance. When you, just like every other chemical reaction, you got to balance everything. You got to balance atoms, you got to balance electrons, you got to balance charge. So all these things have to balance. So if someone's losing 2 electrons, somebody else got to be gaining them. And when you lose them, that's the oxidation. When you gain them, that's the reduction. So what we're going to do is we're going to start with a clear solution of vitamin C. Then we're going to add something that's blue. Now, is it going to stay blue? Will that solution continue to be blue? So I've got a clear solution of vitamin C, and I'm adding a blue molecule to it, the DCPIP. Will that molecule continue to be blue?
No.
No. What's going to happen to it? So if it's not going to be blue, what's going to happen to it? So I'm dropping blue liquid into a clear liquid. Now, if it doesn't stay blue, what happens to these blue molecules? So if you say that if they're not going to be blue anymore, what's going to happen to them? What reaction are they going to undergo?
Oxidation.
So the blue molecules are going to be oxidized? The DC, remember, this is the DCPIP up here. This is the DCPIP. And it's going to be in the oxidized form. And the oxidized form is blue. So if it doesn't, if it changes, is it going to be because it's oxidized or because it's reduced?
It's reduced.
It's being reduced, right? And so when it's being reduced, what happens to it?
It turns clear.
It turns clear, exactly. So I'm going to take a blue liquid and add it to a clear liquid, and it should go from blue, turn clear. Why? Because the vitamin C is being oxidized and giving electrons to my indicator, which is DCPIP. It will go from blue to clear, as long as there's vitamin C there to get oxidized. Now, at some point, I'm going to be adding, drop by drop, I'm going to be adding blue oxidized DCPIP. When will it stop going from blue to clear and remain blue? At what point will it do that? At some point, that reduction reaction is going to stop, and it won't turn clear anymore. When will the reduction reaction stop? Remember, the redox reaction, you can't have reduction without oxidation. The two of them are happening at the same time. One is providing electrons, the other one is taking electrons. So if the reduction reaction stops when one other reaction stops. So these two reactions are linked. My oxidation reaction and my reduction reaction are linked. If the reduction reaction stops, what other reaction also stops?
Oxidation.
Exactly. The reduction reaction stops when the oxidation reaction stops. And the oxidation reaction stops when there ain't nothing left to oxidize. So that means that when the solution remains blue, that means that no more reduction is taking place. Why is no more reduction taking place? Because all of the vitamin C has been oxidized. So once the oxidation reaction stops, the reduction reaction stops too. And so at that point, we will have oxidized all of the vitamin C. So all of the vitamin C will have gone from being in this form over here to being in this form over here. So it will have donated all the electrons that it can. And that's actually what it does in your body too. That's what vitamin C is for. It's a reductant. It adds electrons to reactions that need it. So it keeps things nice and reduced. So once it's oxidized, it's no longer, you can't use it for anything anymore. And so if we know what our concentration of DCPIP is, and we know the volume at which the reduction reaction stops, then we also know what the amount of vitamin C we added, and we can figure out then what the concentration of it is. So we're going to make a standard curve, and the standard curve will just be amounts of vitamin C, and you're going to make I think 4 different concentrations. I think it's 0.5 mg per mil, 1, 1.5, and 2. And then basically you're going to plot that against how much volume of DCPIP is required until it turns blue. Then you'll plot those 1, 2, 3, 4, join them up with a straight line, and see what the relationship is between what the volume of DCPIP you added and the concentration of vitamin C. Okay. So here's how we do the experiment. And like I said, so I'll basically just take you through doing one of these to show you how it works, and then you can do it tomorrow. So we're going to need our ascorbic acid. That's the fancy name for vitamin C. 3 cups. So we're going to make a stock solution of 2 grams per liter, which is the same as 2 milligrams per milliliter. That's the same thing. Now, like it says here, it has to be fresh. So like I said, if you're going to, when you do the experiment, you have to do all of it in one day. So it's a fairly straightforward experiment, so it won't take you very long to do. Anyone see a mistake here in the instructions? Because it says it wants you to make a 2.00 grams per liter solution. And yet it tells you to weigh out 0.5 grams. Anyone see a problem with that? What's the problem there? What's the difference between this number and this number? What's the difference between 2.00 grams per liter and 0.5 grams? Other than they're different numbers. What's another difference between them?
It's not per liter.
Well, yeah, I mean, one's a concentration and one's a mass. That's true, but those are the units. I'm not talking about the units. I'm talking about the numbers. What's the difference between those two numbers? Think scientifically.
The significant figures.
Bingo. Yeah, significant digits. There's only one here, right? There's only one significant digit, 0.5. All it means that it's not 0.6 and it's not 0.4. That's all that means. How many significant digits in this number?
3.
3, exactly. You can't take a mass with just one significant digit and magically turn it into a concentration with 3 significant digits. That's impossible. So what you need to do is don't worry so much about getting exactly 2.00 grams per liter. Do worry about getting this mass accurate. It doesn't have to be exactly 0.5. It could be, 0.497. It could be 0.503. It could be 0.488. But you need to have 3 significant digits to the mass. So then when you make your stock solution, it will also have 3 significant digits. So it doesn't, like I said, it doesn't have to be 2.00. It could be 1.97. It could be 2.03. But make sure you know what that concentration is to 3 significant digits. So without the mass to 3 significant digits, you can't get a concentration to 3, okay? And then you'll take the stock solution and then you'll dilute that. You don't make a new solution each time. You take a solution you've already made and then dilute it. So we weigh out precisely. Oops, go back. You weigh out precisely 0.500 grams or thereabouts. And then we'll dilute that to 250 mils. So because that's a quarter of a liter, that will give you around 2 mgs per mil, or 2 grams per liter. And then that's going to be a stock solution of vitamin C, okay? Then we're going to develop a standard curve. So we're going to use the small Erlenmeyer flask. I think it's the little cute itty bitty one. Put some water in there. And this part is important. Put that on top of a white sheet of paper, because when you do a titration, most titrations involve color change. And it's much easier to see a color change against a white background than it is against a dark background. It's almost impossible to see it against a dark background. So you're going to want to be swirling this over a white piece of paper so you can see, because it'll be blue and then you'll be stirring it and the blue color will go away. And what you want to happen is, if you want to add this, just 1 drop should be the difference between clear and blue. If you go way over, it's going to be like a bright blue color. You want a very, very, very dilute or very light color of blue or green, because the vitamin C is slightly yellow. And when you add yellow and blue, you get green. So you're looking for either a very, very dilute blue or a very, very dilute green. You don't want a bright, bright color. That means you've gone way too far. So, so then we fill our syringe with our solution. Now remember, that is the known concentration of DCPIP. We will have added 100 mils of water to the bottle of DCPIP. And then it's a known, so there's a known amount in there. I believe it's 0.1 grams in there. You add 100 mils, you shake it up, and basically you're going to just use that and then toss it when you're done. So we'll have a known concentration of DCPIP. So you fill the syringe up to 5 mils with that solution. It'll be nice and blue. Make sure you don't have any bubbles in it. And then we put, oh, hi, Edie, you're going? Uh-huh. Okay, have a good trip. Hi. Wife's flying to DC. Not happy about it. So we're going to add different volumes of our stock solution to the small flask and then titrate them, okay? So why don't I just go ahead and show you how that works, and then you can be free. So let me just pause this for a second. I'll move the computer and get set up. So just hang on for a sec. Okay, so this is the bottle of DCPIP, and it says contents, you may not see there, 0.1 grams. So there's 100 milligrams in here, and we're going to add 100 mils of water to it. So you might just want to take it and just sort of just tap it to make sure that, there's not going to be a lot of stuff in here, but if there's any, like if it's been upside down for any length of time, you wouldn't want any of it to escape or to be stuck to the sides of the walls or to be stuck on the cap. So this sort of makes sure that we keep all of it inside. Use your 50 mil flask, listen to me, your cylinder, and add 100 mils. And this you're going to want to get fairly accurate. So use your transfer pipette. Use your transfer pipette to make sure you get exactly 50 in here. So I will get it to precisely 50. There we go. And then I'll just do it again. Oh yeah, you can see these cool blue crystals in here. Should make a really nice, pretty color. there's my first 50. Have a strong smell too. Oops, that's too much. Remember, you always want to get down to the level of the cylinder to read the volume. All right, exactly 50. There we go. And then just give this thing a good shake. And of course, you should be wearing your goggles, which I forgot upstairs. Also might want to wear gloves with this as well, because this is going to be brightly colored. I don't know if it might stain your skin a little bit. And it says right here in the warning that it may cause skin irritation as well. So gloves probably wouldn't be a bad idea. Okay, let's see what color we've got here. Just to give you an idea what it looks like. Oh man, yeah. That is blue. You can see it's an extremely dark blue. So I'll just add a little bit of water to this. Yeah, so this is the sort of, that's the color the solution will be when you've run out of vitamin C. You should basically, you're going to want a dilute blue color, similar to that, okay? All right, so let's make up a solution of vitamin C. So remember, we're going to weigh out precisely half a gram. It doesn't have to be, or accurately half a gram. It doesn't need to be 5.00, but we should know all 3 digits in the mass. Let me get a weigh boat here. And my vitamin C is right here. So this bottle will look like that. See, it has ascorbic acid. Oh, yeah, I just remembered. These balances don't go to 3 significant digits with less than a gram. So you'll get 2 significant digits. All right, so we went a little over. I've got 0.58 grams. So I will use that. I'll use 0.58 grams, meaning that my solution will be a little more concentrated than that. So we're going to be using these glasses to make our solution in. So I'll put my vitamin C in there. And then I want to add, remember, 250 mils of water. So basically I'm going to fill this up 5 times and then dissolve it in this glass. And it should dissolve fairly quickly. Since it's an acid, it should dissolve fairly quickly. All right, that's 1. 2. Three. And 250 should pretty much almost fill that glass. So you got to be kind of careful. Four. Yeah, man, really close to filling it. I don't know why we had to use 250. We could have used 200. And 5. Oh, man. Yeah, so you can see that this pretty much fills that glass right up to the top. So when you stir it, be super careful that you don't spill any. So be kind of gentle when you're stirring this. Now this is going to be my vitamin C stock solutions. This is going to be the highest concentration of vitamin C that we're going to be using. Then we're basically just going to, so we're going to use different amounts of this stock solution diluted with water and add our DCPIP solution to it. And then make a note of how much that solution it takes. Okay. And you check and make sure that everything's dissolved. Again, it helps to have a blank piece of paper underneath. I do not see any crystals in there anymore, so I think it's all dissolved. So we then take, so this will be our first titration. This is the small flask, the 25 ml flask that we're going to use. So we're going to add water to here and our vitamin C solution. So I think we start, let me check and make sure what concentration we start with. Okay. So what I'm going to do is we're going to be using the syringe for both measuring the volume of the vitamin C solution and the DCPIP. So what we're going to be doing is washing it in between. So you're going to want to have something to put waste into, unless you've got 2 of these. So just basically, I'm just going to rinse it out with some water. So I'm just going to draw some water up here. Just make sure there's nothing else in there. So I am going to put So what you're going to want to do is do 4 of these titrations. One with 1/2 ml of vitamin C, one with 1, 1.5, and 2. And then the rest you can just put as much water as you want. It won't really matter how much water you add because we're titrating the moles. Remember, we're titrating the moles of vitamin C. We don't really care what the volume. The volume isn't important. The volume of vitamin C solution we add is important, but the total volume that we put in this flask is not important. Why? Because it's moles of DCPIP versus moles of vitamin C. The actual, that's going to be the reaction. The actual volume won't matter, but you need to know the volume of the vitamin C solution to compare to the volume of your DCPIP solution. So I'm just going to go right ahead and do the 2 mils reaction. So I'm going to draw up some of my vitamin C. Now I'm going to want to take more than I need, because there's going to be probably an air bubble. You can see there's an air bubble here. I want to get rid of that. So just like you're giving an injection, you want to make sure there's no air in there. And then, oh, got another air bubble. There we go, get rid of that. Okay. Now we want to get it to the 2 mil mark. You can see now it's around 3. Push that till it gets to 2, and then we'll put that in the so there is a line, there's 2 lines here. You see there's 2 lines on the rubber, one below and one closer to the end. So line that up so that it says exactly 2. And then we're going to put that in our 25 mil. And then remember, rinse this because it's got vitamin C in it. So I want to make sure I rinse all that out. So rinse it out with water, like 2 or 3 times. Now the way we're going to handle the DCPIP solution is slightly different because we don't know how much we're going to need. So basically we're going to draw out our DCPIP solution to 5. Make sure this lines up exactly with 5 mils, right? So have exactly 5 mils in there, and that's going to be our starting volume. And then we'll keep adding DCPIP until it stops turning clear, and then you get the slight blue, or this will probably be a slightly green color. And then we'll subtract the volume that's left and figure out that's how much volume we would have used. So make sure I get all the water out. And then fill this to 5. It should be very dark color. Oh man, is it ever. Yeah, you can see how dark that is. That is dark. So this is going to be messy. So I've already got blue fingers. So yeah, this is going to be messy. I would suggest putting down some newspaper or something like that. I got some like shop towels down so I don't stain anything. So and it's also going to be a little tricky to read the volume, right? Since this is so dark. So I want to get all the bubbles out. And get it to 5 mils. Okay. All right, so I've got it at 5. All right, so I get a white sheet of paper. So you can see this for yourself. So I've got my solution here. So remember, this is my oxidized molecule. I'm going to be adding it to my reduced molecule, which is in here. Now the reduced molecule, which is the vitamin C, is not going to change color. This is. So let's see what happens when we start adding. I could also add a little bit more water, just to make the mixing a little easier. Then make sure I've got all my solution at the bottom. Okay, there we go. Now what, did you notice what happened? Were you able to see it? It was blue, and then as soon as it hit it changed, it went clear again, right? So basically what we're going to do is keep adding this drop by drop until it stops going clear. Now notice there's a little bit of blue in there, but we swirl it around, it goes clear. That's because there's going to be, without mixing, there's going to be like just small little bits of area where you have unreacted molecules. But when you mix it up, they'll react. So you want to go drop by drop here. You don't want to add a whole lot at a time. So you see I got a drop on the side, so I want to make sure I get that. I swirl it and it goes clear. So I just keep going. Oops. So you can see there's a little bit of blue in there. Swirl it around. Oh, well, still got a ways to go. And we got dogs upstairs barking their fool heads off. I can also see a little bit of yellow. It probably won't show up on the camera, but you can see a little bit of yellow in there from the vitamin C. So I'm thinking this might turn green. Yeah, it's kind of hard to see, but it's a little, I don't know if you can, it's a little bit yellow. So I think we may get a green color rather than a blue color. And remember, this is the highest amount of the vitamin C, so it probably will be slightly yellow. A little bit on the side, make sure I get all that in there. Yep, so I'm still not there yet. And after your first titration, you'll have a pretty good idea of how much volume it will take. So basically, once I've done my 2 mils, and the next one I do is the 1.5, I'll know it should take approximately 75% of the same volume, right? So again, there it goes back. So I've used about 2.5 mils so far. I'm still not there. But one thing you'll notice as you're doing this is that when you first start, the blue will disappear immediately. Now you see this sort of hanging around a little bit more. And as it hangs around a little bit more, that sort of tells you that you're getting close to the equivalence point. And the equivalence point is when the moles of DCPIP equal moles of vitamin C, and then you're done. Yeah, that yellow color is becoming a lot more pronounced now. So I definitely think we're going to get a green. A nice green color rather than a blue. Oh man, it's getting really yellow, right? You can now it's becoming a lot more obvious. So I think what we're going to be looking, yeah. So we're going to be looking for a light green color that doesn't, that when you swirl it, it doesn't change. There's probably only be just a couple more drops now. Oh man, yeah, this color is probably just 1 or 2 more drops. We should be there. All right. why it helps to have a little bit more volume in here, because that makes the mixing a lot easier. All right. So it takes a while because you definitely want to go drop by drop. That's sort of the secret to a really good titration, is you want to be just basically like half a drop over and no more. I'm just going to basically be adding like 2 drops at a time now. Still not quite. Not quite, still yellow. Man, I'm almost done. I almost don't have any left. Oops, I spilled some on the side. Oops. 2. Nice. I got some on the side. So I have to, so that's an error that I will make. I spilled about maybe a tenth of a mil. Oh man, we're so close. It looks like it's gonna take pretty much the whole 5. Because it's taking longer and longer for that color to go away. Man. That has used up all of it. So it could be that it's that yellow color. It's this dark yellow, I think it's probably the color we were looking for all along. That may be something that they could have explained better. Something they could have explained better in the original instructions. So what I'm going to do, I'm going to try this again with half a mil and see if it works. See if it works any different. Because I think what we're looking for with a high concentration of vitamin C, I think it's this bright yellow color we're looking for, because it wasn't this color when we started. So let me try that again with a smaller concentration. It's a good thing I did this first, because that would have been very confusing. Because it says to look for a green color, and I don't think it's a green color we're looking for. I think it's that gold color. Okay, let's do a quick and dirty one here. You want to rinse all of the DCPIP out of your syringe. Also might have helped if we got 2 of these rather than 1. This time I'm just going to add some water. And then I'm going to add half a mil of my vitamin C solution. So get all the air bubbles out. There we go. Yeah, I'll do 1. So 1 mil of vitamin C. There we go. So half the volume we used last time. So I want to see if we get the gold color or the blue or green color. Okay. So now I add DCPIP. Okay, there we got 5. All right. Let's see if we get a different color this time. So it's hard to see, but it does sort of turn a yellow color before it goes clear. So I think it is that yellow color we're looking for, which is a little misleading. Because right around the blue, you can see just these tinges of yellow. And then it goes away. Swirl it, it's gone. Yeah, so again, I've got this yellow color. Let's see. So make a note of that volume. When you get that persistent yellow color, make a note of that volume. Because to be honest, I'm not sure if that's the color we're looking for. Now I'm going to keep adding and see if it gives us that green. Again, just getting a little darker yellow. Again, disappears. Much darker yellow color. That took a while to disappear. There we go. Oh. What may have happened is that I went a little over, when I was making the vitamin C solution, I went a little over, right? I think I had like 0.58 grams rather than 0.50. So I think you might want not to go over, maybe the secret here. Because all these experiments are designed to use the volumes that we've got here. So it could be that half a gram of vitamin C in the solution will equal 5 mils. And if I went over, then I'll need more than 5 mils. There we go. Yeah. Oh man. Just did disappear again. So I think I'm about 1 or 2 drops. Yep, goes back to yellow again. Oh, I think there it is. You can see it's definitely a different color now. But it goes back to yellow. So desperately looking for the color. So you see it turns this light blue, kind of green color, and you continue to swirl it, and now it's not changing back. Okay, so man, this is going to be tricky. So it's this color you're looking for. It's I don't know if you can see that, but it's really, really close to green. So see if I can get it to be green. It is super close to this yellow color. So you can see it turns blue. Your whole thing is blue. And you continue to swirl it. And you continue to swirl it. And that's it. Yeah. So that's the color here. So you're looking for this sort of dark yellowy green color, because I continue to swirl it and it does not change. It is not changing color. So that's the color you're looking for. I may have even gone like a drop or two over. That's the color you're looking for. It is a sort of, you get a bright yellow and then it turns blue, and then you mix it up and you get this sort of aqua, sort of blue-green color, sort of this dark teal color. And that's the color you're looking for. So we would make, so I think the problem was, yeah, I went over. I used more than half a gram. I think that apparently that's really important. So we would make, so use, if you're gonna, don't go over. That appears to be the case. So that was my 1 mil, and it took me almost 4 mils of my solution for it to change color. So maybe even less than half a gram is important. Because if you use more than 5, just refill this and keep going. That's the important thing. So that's the color we're looking for. So basically that is the experiment. And let's just briefly look at how we will deal with the data, okay? And call it a night. Because man, it's already 10 o'clock. This is ridiculous. So, so you make a note of the precise mass of the vitamin C. You then calculate the concentration of vitamin C to 2 significant digits, because that's how many we get in our mass. Be really careful about adding the dye. Wear gloves, because you can see I've got blue all over the place. And put a lot of papers down, because yeah, this is messy stuff. I didn't realize how messy it was going to be. So when it's time to do your calculation, this is what your graph is going to look like, right? So what we're going to do, so here's the data you're going to be putting in. So 0, half a gram per liter, 1, 2, 3, and then how much volume you used of the super blue DCPIP. So my instance for the 1, I used like 3.5 mils, I think. And then so basically what you'll be plotting, and then for your unknown, basically your unknown is basically just a dilution of the stock solution that you'll make. Just dilute it to something. Dilute it to something between 0 and 2. So basically pick any dilute, fill it, take the 50 mil cylinder and put like 10 in it or 40 in it or 30 in it. Make a note of what it is, and then dilute the rest with water up to 50. And then you're going to repeat that 3 times. Basically, this is just a test of how accurately you can do the experiment. Oops, didn't want to do that. Okay, so when you do your plot is going to look like this. So you're going to put your concentration of vitamin C down here in grams per liter or mgs per mil, it's the same thing. And then over here will be milliliters of DCPIP. So hopefully you'll have a fairly, straight looking line. And then when you plot it with Excel or whatever it is you're going to do, you're going to get a y equals mx plus b plot, right? Because this is linear. So m is the slope and m is the change in y over the change in x. So basically you're going to get the change in mils of DCPIP over the change in the concentration of vitamin C. So that line, that slope of that line, will tell you what the relationship is between this and this. So basically all you need to do is just use the slope of this line to relate these two things. And then you use mils of DCPIP to calculate your concentration of vitamin C for your unknown. And that's it. So it's a fairly straightforward experiment. It's messy. That change in color is tricky. Remember, as you noticed, it was clear, and then it got yellow, and then it got really yellow, and then you get this sort of greenish, almost like a bronze green color. You want to get as close to that yellow color as possible. Basically, you just want to have like one drop added, and it changes color and then it stops. So be constantly stirring, always be swirling that around. So I think I've kept you guys long enough. If you got any questions about how to do this or how to report your answers. I think the last thing here, they asked you what the trend line is. That's basically your y equals mx plus b. It's asking what's the slope, and then you use the slope to calculate your concentration of 1, 2, and 3. And you should get relatively the same answer, obviously, because you're using the same dilution. But when we do this sort of work, we always do things in triplicate because if we get an answer of like, let's say 2.0, 2.0, and 1.1, we pretty much know that this one is an outlier and this is the answer we're looking for. So that's why we always do things in triplicate. Sometimes we do things in quadruplicate, but generally in triplicate. Because so if you make a mistake, it doesn't get factored into the final answer. And we all make mistakes. I mean, hell, you saw what I did here. So I think the key is using less than 0.5 grams of vitamin C. I think that probably will help. And yeah, just being really careful with your titration and wear gloves. So sorry, any questions?